midterm exam. I handed over the standard solution to TA this evening, so he can start checking your answer sheet. And today we will have a coastal process. So we will start the second textbook today. And Sung-ho Choi will lead us the first lecture and myself. And one small change is that Melissara will have a discussion tomorrow afternoon, so that I will have another lecture over for the Tuesday. So we will have 3 short lectures today, and then tomorrow we will have 1 lecture and 2 discussions. All right. So, any other questions on schedule? No. And we can go on to Sungho's lecture. Let me make you share your screen.
잘 들리시나요?
네.
Okay, let's start. Good afternoon. My name is Seung-ho Choi. And today I will talk about coastal process and structures. This is the list of today's contents. I will talk about these first 3 parts. And hint casting, secondary flow, Ekman spiral, upwelling, lip currents, global currents, loop currents, and gyres. Hint casting is a way of testing a mathematical model. Hint casting is also known as backtesting. Known or closely estimated inputs for past events are entered into the model to see how well the output matches the known result. And this schematic shows the difference of hint casting and forecasting. In fluid dynamics, flow can be decomposed into primary and secondary flow. The secondary flow is a relatively weaker flow pattern superimposed on the stronger primary flow pattern. This is the primary flow pattern. The secondary flow usefully spotlights the effects of complicated real-world flow neglected in primary flow pattern. A classic example is the teacup experiment. If one stirs the tea so as to give it a generally circular motion, the tea leaves invariably gather at the center of the bottom of the cup by the secondary flow. And I will show you a short video about teacup experiment.
It did not share the sound when you're sharing the screen. You need to check the box at the bottom
Okay,
to share the audio.
洗いは止まりましたけど、中の水は惰性
can you hear?
でまだ回転を続けています。これをしばらく観察していくと、下に沈んでるお茶っ葉はだんだん内側の方に集まってくるというのが分かります。これは二次流れという現象によって起こるものです。二次流れとはもともと遠心力で水は回っているわけですけど、そこに近いところは流れの速度が遅くなります。これは粘性の影響によって容器を止めると、その容器と同じように流れが遅くなると。流れの遅い底の部分の水は遠心力が弱まりますので、内側の方に流れていく、そういう流れができます。一方、水面から少し離れた水面の上の方、近いところとか真ん中あたり、これは遠心力の影響で、中心が集まった分だけ外側の方の流れができます。
And the flow pattern is different according to the depth. And this video shows the flow is different according to the depth.
With this, I can trace the flow and see where it goes. Let's try a little at the surface to see what's happening. At this rate, it'll be a long time reaching the drain. Maybe it never will. So much for surface flow. Let's start over. This time, we'll try injecting at about half depth. Again, the pattern seems to be one of nearly circular flow. The water going out of the drain must come from the bottom. A small spur holds the tip of the needle about 1/8 of an inch off the bottom. We can see that the dye goes rapidly toward the center, and this seems to be the answer to our question.
The Ekman spiral is the result of a force balance created by a wind shear stress force and Coriolis force and water drag. This force balance gives a resulting current of the water different from the wind. This surface current is 45 degrees and net water transport is 19 degrees. At the surface of the ocean, where the shear stress force needed corresponds with the wind stress force, and at the bottom of the ocean, where the shear stress force is created by friction with the ocean floor. By this Ekman spiral, the oceanic phenomenon, upwelling and downwelling, is induced. Upwelling is the movement of deep water to surface. It transports cold nutrient-rich water to surface and produce high productivities and abundant marine life. Downwelling has opposite wind direction, and surface water goes to downward. It transports warm and non-nutrient water to surface, and it is not associated with high productivity and abundant marine life. And this is another examples of upwelling. First example is induced by offshore wind. The surface water goes offshore and the pressure decreases. So deep water goes upward. In second example, the table mount blocks the portion of current flow and makes upwelling. In last example, the sharp bend in coastline makes the low pressure region in surface, so upwelling occurs in this region. And Langmuir circulation is transient response to impulsive wind forcing, where helical vortices form near the sea surface. There are numerous long parallel lines or streaks, and the streaks are formed by the convergence caused by vortices. The lines can be many kilometers long. Note that Ekman's theory of the wind drift yields an upper layer motion that is about 45 degrees to the right of the wind. However, Langmuir circulations are more closely aligned with the wind. Rip current is a kind of water current that can occur near beaches and with breaking waves. It is strong, localized, and narrow current of water which moves directly away from the shore. This video shows about rip current.
You might have heard them referred to as undertow or riptides, but these ocean phenomena are actually rip currents. Rip currents are narrow currents in the surf zone that move quickly away from shore. A typical rip current ranges from 50 to 100 feet wide and can extend 100 yards or more offshore. It can reach speeds of over 5 miles per hour. That's faster than an Olympic swimmer. That makes them dangerous and potentially deadly, and scientists want to learn more about them so we can better forecast when and where they will form and keep beachgoers safe. Here's what we know. Waves don't have to be huge for a rip current to form. 2 or 3 feet are all it takes. And the weather doesn't have to be bad for a rip current to emerge. They often occur in the nice days after a storm. They're usually strongest near low tide, but can form at any time. Rip currents often form where sandbars are near the shore. They occur at breaks or channels in the bar. They're often difficult to see, but you can spot them in areas where waves aren't breaking or where there's foam, seaweed, or discolored water being pulled offshore. It's easier to see a rip current from higher up, such as from the beach access over dunes or a lifeguard's tower. Rip currents are a hazard for beachgoers, but by knowing the dangers and what to look for, you can avoid being caught in the grip of the rip.
Rip currents are wave energy escaping shoreline. It stream of water returning out to sea through surf zone and flows up to a few hundred meters offshore, then dissipate. Along-shore current refers to ocean current that travels parallel to the shore. In comparison to other types of currents, the longshore current is most often located close to the shoreline. As sand, sediments, and other objects move onto and offshore by angled waves. They are carried down the shores as a result of the longshore current. The sea has a greater heat capacity than land, so the surface of the sea warms up more slowly than the surface of the land. As the temperature of the surface of the land rises, the land heats the air above it and by convection. The warming air expands and becomes less dense, decreasing the pressure over the land near the coast. The air above the sea has a relatively higher pressure, causing air near the coast to flow toward the lower pressure over land. In the night, the temperature of the air above the sea is higher, so the direction of wind is opposite. And this is about global ocean simulation.
Also, there is no sound.
Oh yeah, this video has no sound originally. And ocean mesoscale eddies are the weather of the ocean, with typical horizontal scales of less than 100 kilometers and time scales on the order of a month. The mesoscale field is characterized by temperature and salinity. Mesoscale eddies are ubiquitous in the ocean and exhibit different properties to their surroundings, such as heat, salt, and carbon around the ocean. The loop current is a warm ocean current that flows northward between Cuba and the Yucatan Peninsula, moves north into the Gulf of Mexico, loops east and south before exiting to the east through the Florida and joining the Gulf Stream. This is the ocean current in the Gulf of Mexico as depicted by the US Navy. Colors represent the speed of the current in centimeters per second. And SST means sea surface temperature. This is the example of SST simulation. And this is the last video about gyres.
So a gyre is a natural phenomenon. A gyre is simply a rotating current system that's comprised of the Earth's rotation coupled with currents and prevailing winds. So it's essentially like a massive whirlpool, a vortex in the oceans. Say a piece of floating plastic from California in the North Pacific Gyre can take 10 years to make the rotation from California to Japan and all the way back.
So what we have found is that these plastic particles are not just in the North Pacific Gyre, they're in all 5 subtropical gyres, and all these gyres have several garbage patches in them, 8 garbage patches total in the 5 gyres.
So that was our inspiration to start the 5 Gyres Institute, to look at this plastic pollution issue on a global scale and try and show the world this is an international problem. These plastics are coming from every continent in the world, and solutions have to be on the international level. When I first heard this talk in 2001 from Captain Moore, I heard description of an island of garbage that people were calling the Great Pacific Garbage Patch. In the media, it was described as a Texas-sized island.
It's really hard to quantify how much plastic is floating in the world's oceans. These garbage patches that exist in the gyres, they're elusive, they change shape, they move around. You may trawl for 10 hours straight, you'll get a handful of plastic. You put it back in, 10 hours more, and there's nothing.
So it's essentially like a plastic soup of all of this disposable waste that we create on land masses, from California to Asia, Canada, Mexico, enters this North Pacific Gyre and gets swept up into this accumulation zone.
Islands in the gyres we're discovering are the natural nets for trash at sea. It's impractical to try and scoop out trash out of the ocean. What we can do is wait for it to wash ashore. So to clean a gyre, clean your beach, clean your watershed, clean your street. As close you can get to the source is a better way we can solve the problem of plastics in the ocean.
Okay, thank you so much. Any questions? No? Okay, I will finish.
Okay, thank you very much. It is just on time. Good. So we may have a 5-minute break. So we come back at 9 o'clock. All right.